So my name's Mark Stickles, I'm the director of Pawsey, and welcome to Pawsey Friday. So our colleague Avitya is a physical oceanographer from UWA with more than 15 years of experience in numerical modelling and ocean observing systems. I think the title, from the Rottnest Swim Ocean Forecast, the better prediction of tropical cyclones, has obviously garnered some interest today, and really interested to hear from Avitya and his presentation this afternoon. So join me in welcoming him. Thank you.
Thanks. Thanks for having me here. So I'm going to talk a little bit about the numerical modeling of the atmosphere and the ocean and the interface between them, and show you a few examples where these things can be really important. So I'm going to talk mostly about the ocean modeling, and from ocean modeling I mean numerical modeling. I'm just going to tell you a few stories about historical development of the ocean modeling, and then we'll jump on the Western Australia modeling actually and show you what we are doing at University of Western Australia and a few examples of advanced modeling techniques that we are using and using your Magnus at the Pawsey as well. So just to tell you about the numerical modeling in the physical oceanography, it's a relatively new component of the physical oceanography. Physical oceanography is really old discipline, but numerical modeling is kind of considered as a separate part of the physical oceanography nowadays. And you can think of that as the younger brother of the atmosphere physics. So before like 10 or 20 years, we were lagging behind the atmospherical science, about 20 years. So the stuff which they developed for the atmosphere, we waited for like 20 years to be implemented in the ocean. But nowadays we are kind of catching up, and I would say that we are roughly 5 years behind the atmospherical science. So they're still having the better models, better tools than we do, but that gap is actually getting closer and closer. From theoretical point of view, foundations are really well known more than 100 years ago, and definitely when we are talking about the physical oceanography and numerical modeling and the atmosphere as well, we have to tell something about the Bjerknes, who was actually the father of the atmospherical science in modern sense. So he was the guy, really cool guy. Actually, he was studying in, I think, Bonn with the Hertz on the resonance. So he was a real physicist. And after that, he was the founder of famous Bergen School of Meteorology, who was actually growing up all these famous meteorologists in 50s who started the numerical weather predictions. So he was the one who wrote down the equations that we are using today, actually, for solving the partial differential equations. After him, definitely we should say something about the Richardson, who was the first guy actually doing the numerical prediction or weather prediction in 1922. He published that famous paper. And he was really extraordinary person. He was pacifist. He didn't want to go to the war. He didn't want to fight. So they sent him during the First World War to kind of medical, let's say, division somewhere. So he had lots of time. And he was computing numerical predictions by hand, actually. And it took him around 6 weeks to compute the pressure tendencies for this grid. This is his famous checkboard of the Central Europe, basically. And he was computing, let's say, first weather prediction, and he failed miserably. He got results like 100 millibars tendency, which is never going to happen, you know. And the problem was not actually in the way how he solved that. The problem was in the initial state he used. He didn't use the smoothed fields. He used the draw measurements, and that's why he failed. But he was really kind of cool guy. And he was the first person actually thinking about the computers, in sense. For him, computer was the person who is making computations. So in that sense, like, he would imagine that you have one central point, actually central unit, who is looking on that globe. And each of these globes you will have kind of computers, which are people doing calculations. And this guy was pointing with the light on each of these boxes. He would like to have information and synchronize information in the central unit. So this is basically what we are using now in MPI kind of paradigm in supercomputers. Basically, you have master node, MPI, send, receive. I mean, this was idea that that guy had long time ago in 1920s. And he said that for kind of real focus, he would like to have, I think, 64,000 people computing at that time to get it in real time. So, I mean, now we are really far away from that. So as I said, like physical oceanography was stepping as the computers were basically developed more and more. So in that sense, the first computer that was used for numerical weather prediction was the ENIAC, which was actually the beast, you know. And probably you know that it had like 5,000 simple operations per second, like adding or you know, taking off, and 385 multiplications per second, and it used like 140 kilowatts, you know, of the power. So it was kind of amazing stuff. And then you had the Cray in 90s. Yeah, huge step. Again, using like 128 kilowatts, and it costs around $15 million, you know. And nowadays you have something like this, which is Raspberry Pi. You probably know. You know, it's ARC. It has like 4 cores, and it can get 357 megaflops peak performance, and it's using only 1.2 watts. You know, so in that sense, we are really kind of stepping into the new era. And like somebody did kind of comparison from 50s, if you have a car who was driving like 100 kilometers per hour, and today's supercomputers, the development was so fast that that car should go almost the speed of light today, if you follow the trend in the computers, kind of how they developed in time. So now we are actually here. We are at the Magnus, which is kind of in the zone of pentaflops, you know. And the question is, are we really going to go probably further? Because the Moore law is, somebody saying, hitting the limit, because you can't put any more tensed CPUs. Now they're using 12 nanometers, I believe, or even less. So, I mean, this is amazing. You know, they're at the scale of the atom, you know, and they cannot put even more. So they're probably thinking to go in 3D. So now future chips are going to not be built anymore in 2D, but in 3D. So anyway, it's really challenging time that we are actually living in. So if you want to do any kind of global numerical modeling, for example, atmosphere, there are big players on the scene, like ECMWF, which is European Center for Medium Weather Forecast. It is using that EIFS, which is kind of advanced atmospherical model. And nowadays they're running the whole world at 9 kilometers. You know, it's kind of, you don't have to run local models almost anymore, because they are so powerful. They can run the global models at those high resolutions. In US you have GFS, which is around 25 kilometers, but over the US they're running the high resolution. In Australia you have Access run in BOM, but unfortunately many of them are really not freely available. So those with red arrows you can't download easily in let's say in focus mode. If you want to do your focus on or get the raw data, only you can download is actually GFS model. In the ocean we have HICOM model, which is global model again, at 1/25th of a degree. And in Australia we have Blue Link as well. So, but if you want to go to super high resolutions around Australia, you have to do your modeling. So what we are doing is actually we are using those global models to provide boundary conditions for our local high resolution models. And those boundary conditions you can think of like the windows. So the local model knows what is happening outside through those boundary conditions, which you apply every hour or so. If you want to model the Australia, it's really complicated because we have really steep bathymetry. So all these models are pushed to the limits at that kind of high slope you can see on the shelf. So it's not easy to do it. And I'm just going to show you a few examples for the Western Australia that we are doing at the uni. So if you concentrate on this area, blue box, so this is, for example, the results of our ocean model, who is having 2 kilometer resolution. on the western coast. Left is temperature, the right is salinity. It has 2 kilometer resolution spatially and 25 vertical levels. And in that red box, actually, we are running the nested model at 500 meters around the Perth. So the big model is so-called parent model. It provides the boundary conditions for that small, fine 500 meters resolution model. And we can do actually the forecasts. So this is 500 meter resolution of the Perth area with Rottnest. So you can see all this fancy stuff happening around the Rottnest, island wakes, and all physics that is missing, not only on the global models, but on those 2 kilometer models as well. So in order to force that model, you have to put some atmospherical forcing. So you need the atmosphere to drive the motions in the ocean. So for that case, we are running the atmospheric model, which is called WRF, at 10 kilometer over the whole region, and then we have, again, zoom around the Perth at the, I think, 2 kilometer. So those two models are actually seeing each other and providing information back and forth. With those models, you can actually predict something what happened like this. If you remember in 2014, we had that crash of the big ship at the railway bridge in Fremantle, which actually detached from the mooring and hit the bridge. So the reason for that was something like this. So we had that so-called meteor tsunami, which is when you have pressure perturbation in the atmosphere traveling at close speed to the resonance in the ocean, then it's pumping the energy in the ocean all the way as it travels and induce pretty big currents. So this is just an example how we can actually model such events. The top panel is showing you the sea level measurements and the model kind of estimate at Hillary's Harbor, for example. And the bottom is one showing you the wind speed in the atmospheric model and the pressure drop. So this guy was actually responsible. This small kind of pressure perturbation was strong enough to create that huge meteor tsunami, which actually caused really strong currents. And as we run the model in the house, we can save the results at resolution of 12 seconds. So every 12 seconds, we have information about the wind, about the pressure, and we can capture all these kind of jumps. Another example of the front coming later on with all these strong winds and these glitches in pressure field, those are really dangerous for Western Coast and Perth. So all the results are available, so you can grab the data. I'm putting the data on the opened up server on the threads, so it's, you know, if you want to use it, it's like 5 lines. You can get directly to the raw data. We are putting the data on the web as well. It's called coastaloceanography.org. So you can get the latest, let's say, forecast for the atmosphere. This is results from the WRF temperature. You can see the front coming. This is synthetic, the reflectivity. The response in the ocean, in surface currents, you know, in salinity, and everything is fed to that 500 meter coastal small fine domain around the Perth. So at the end, you can have the currents around the Perth at super high resolution. And this is actually all available online. And this is how we get to the Rottnest, which I promised in the title. So not to kind of miss that. So you know that every year they're swimming from Cottesloe to Rottnest around 20 kilometers. You know? So as we are running the model in real time and providing the focus, so we were able to give them like 4 days in advance the current fields and other state variables that they were interested in. So in CSIRO, they used some kind of optimizing route tool, which was fed by our currents. So you could actually get the idea how you should swim to get, let's say, through the best route to the Rottnest. So for example, if you have really strong currents pushing you north, if you choose the northern path, you will be kind of swept away and never probably get to the Rottnest. So in that way, you should actually use the, oops, it's sensitive. So you should use basically southern part, and then the currents are pushing you all the way up to the north. So in that sense, you can optimize how you can swim. And this is just example, but search and rescue can use that. Oil spill, a lot of other kind of more serious stuff can use all these data as well. So on the website, we are predicting something like this. So you get currents in time, so you know those are markers where they swim. So they should know what to expect actually on the way. And then we step into another. So you can do all that on simple computers, on workstations basically. And if you want to go to the data assimilation, then you can't use any more normal computers. You have to use something like Magnus. So this is like at least 30 times more expensive than the normal simulations. So in that sense, like for example, you can have on the right side observations from the satellite, for example, sea surface temperature, and you have some idea about the model on the left. So, for example, you concentrate on those stars. You can see the model is too warm if you compare it to the real observations. So we say that, for example, if you have surface temperature, you have B is background, your idea what is happening in the ocean with your nonlinear model. Then you have some observations, and your model is not really going through those observations. It's kind of having errors like this. And then you would like to have some super technology, which is assimilating everything, run on a supercomputer and give you the best estimate combining those observations and the model dynamics at the same time. So this is kind of our plan. So not so naive approach is actually through the equations. I'm not going to slaughter you by that, but only just to show you what we are solving. We are solving a problem about 38 million points each time step. So you can't.
I had a question on
yeah,
that.
sure. About the equations. So I mean, if you want, I can spend more time explaining. But anyways, so this is kind of what we are solving on the Magnus, basically. And this is not really big grid. It's kind of 2-kilometer grid only for Western Australia. So in that sense, if you spread it on 192 CPUs, each actually CPU is crunching 2,100 operations per second. So in that way, this is the only way how you can solve that kind of problem. And what we are assimilating everything you can get. So the resistance is futile. In that sense, we can assimilate the gliders, which are flying through the water, up and down, measuring the temperature salinity. We are assimilating the current meters along those transects, which are deployed by the ship. We are assimilating the gliders dropped from the ships. We are assimilating the high-frequency radars, which are at the Cottesloe Beach, measuring the surface currents. All the satellite data, everything is inside the model. One example, in 4-day assimilation, we assimilate around 2.5 million observations, just to improve our estimate of the ocean state. So, and it takes like 5 hours on Magnus. So 5 hours on Magnus for 4 days focused, which is kind of still doable. We can speed it up, but not really to get like 10 minutes or something. So this is the idea. So you had before some kind of estimate of the ocean, you assimilated a whole bunch of data, and you get the posterior estimate, which is similar to this one, but there is a difference, So this is the difference between what assimilation is telling you and what you knew before, basically. And you can then slice it down. You can see, okay, this was my error before this curve, and those are the assimilated observations, and this is what I had after. So you can see that actually you're reducing the error of the model almost twice and getting closer. And what we were trying to do is kind of, we tried to speed it up. So in that sense, we were trying to estimate what is the speed up curve here on Magnus. So if you subdivide your domain on small tiles and spread it with MPI, for example, you get up kind of saturation, because the communication between the nodes are taking actually more time than the pure computations. So in that sense, I don't know, like at 96 CPUs, you get almost linear speed up. You're not losing anything on communication. But in this case, for example, you can use 384 CPUs, but you get only half of the speed up. So in that sense, you can't really speed up the model to 10 minutes. You're still kind of suffering from the communications in that sense. And about the last topic, can we improve the tropical cyclones? So as far as I know, currently BOM is not using any information from the ocean. So for that, it's kind of amazing. But this is how it is. So they're not using any ocean. But we know actually the ocean is responsible for development and growth of the tropical cyclones because they're feeding from the heat content in the surface layer. So, and probably that's why the tropical cyclones are too strong, which shouldn't happen. But not only the ocean from the temperature, but that they're not using the waves that are changing the roughness of the ocean, which is actually then again imposing the problem in the atmosphere. And I was trying to simulate those tropical cyclones with 10 kilometers just to see if it's possible or not. So in that sense, this is what I've done. So I was running the big atmospheric model for that tropical cyclone Olvin in 2015. And at the same time, I was running the ocean model. And both of them actually were run here on Magnus, and I used 480 CPUs. So atmosphere took half, 240, and the ocean, which is ROMS, is hydrodynamic model, and WaveWatch 3 is the wave model. So they both use other half. And actually, I could simulate in 10 minutes one day of the real stuff happening in the nature. So, and what is the important, all three models saw each other every 10 minutes. So they were exchanging all the information between the ocean and the atmosphere. So this is set up for the northern shelf of the Australia. So this is ROM's model, hydrodynamical one, at 2 kilometers almost, having all these features like surface heat flux, tides. So you can see actually the tides propagating here and developing all these eddies. So all these scales are inside the model. And if you go to in a vertical, you can predict the internal tides as well, which is important for gas and oil industry, for the pipes and all that.
I was just going to observe slide 4.
Yep.
There's a Prelude is a $20 billion dot.
So Prelude is kind of the largest floating LNG built, and I think their operations per day are estimated around $30 million. So one day they're not working, they're losing 30 millions.
It's a vessel designed.
Yeah, it's a vessel almost.
To ride through
Yeah, it's like 500 meters, I think, long vessel anchorage there, and it's huge. It's, I think, biggest ever built. Yeah, so you can actually estimate all these parameters using that kind of model at those locations. In the atmosphere, this is how that all in the model looks like. So this is the humidity of the core of the in the WRF model. So this atmospheric model, if you just use atmospheric model and see how the winds looks like, you get something like this, which is too strong in a sense. So WRF predicted too strong tropical cyclone, having too strong winds. Which is not really surprised because it didn't see anything what happened in the ocean. So if you're running the ocean model and you use that kind of information from the atmosphere, you get super cold water here because the tropical cyclone was eating all the heat from the ocean and cooling up the surface. And as the ROMS didn't send any information back to the atmosphere, he didn't know that he actually used all the available energy. So he was hanging there and growing and growing and growing and getting speed which is too strong, basically. So if you use the, let's say, 6-way coupled models, because you have 3 models and they're all 2-way coupled. So for example, wave model is sending you roughness to the atmosphere, and the atmospheric model can see, okay, I don't have flat surface, I have waves. They're defining the turbulence differently. And then that guy is sending the better estimate of the winds back to the waves. So the waves are better computed in the next step. At the same time, the atmosphere is sending information about the heat flux and momentum to the hydrodynamical model. which is sending back surface temperature to the atmosphere. So he knows what he has to consume to develop, basically. And these guys are communicating as well. So you have 3 models talking to each other every 10 minutes and sending information between them. So the bottleneck here is communication in the supercomputer, in a sense. And then you don't have that super cold dome developing there, because the tropical cyclone cannot hang there anymore because he ate already all the heat and had to move on. So in that sense, for example, you can see the development of the waves. So this is the wave response, significant wave height during that tropical cyclone, which is two-way coupled to all other models. So we had like over 7-meter significant wave height waves passing through that. This is big Woodside, North Rankin kind of facility. So, and they were actually measuring all that. So if you compare these 2 scenarios, the top panel will give you how the storm looks like if you use two-way coupled 3 models on the left. And this is the curve where actually the storm was going through. And the white star is showing you where it should be. And on the right side as well. And if you don't use two-way coupled models, you have 2 strong winds actually lagging behind. So it's still, more to the north. It should be here at the white. And it's definitely too strong. Because he was hanging there, having enough energy, feeding, and he didn't have to move, basically. So, and response similar in the current fields. So if you compare that with the observations, so this is satellite measured escat winds with some kind of altimeters passing by and 2 different time. So this is the 11th of March, this is 12th of March. This is uncoupled case, too strong, definitely. And this is the coupled, having the velocities much closer to basically to the observations. And just to drop you some conclusions, one famous mathematician said that actually all models are wrong, but some are useful, and I would agree with that. Because they will always be approximation of the real time, of the real systems. And we do all such simplifications in the model, not only in the solving the equations, but in parameterization and so on. So, and it's kind of really surprised that you get that good results at the end. Taking all these information that you have neglected before. But not only for forecast, you can use the models to give you idea about the sensitivity of the systems, for example. If you want to create the new observation network, the model can tell you, well, you should measure there, because I don't know what is happening there. So to reduce my error in data assimilation, I should get observations at those locations. And if you're measuring somewhere where the model is already good, then there is no point in doing the measurements there. And the measurements in the oceans are extremely expensive. So we are talking about the millions, about the experiments. And regarding the tropical cyclones, you have to use two-way coupled models. This is what we figured out from that study. So if you don't use feedback from the ocean, your atmospheric model is basically lacking lots of information holding in the ocean and getting inappropriate winds. And on the Australia, it's especially true. Lots of dollars are spent on the northern shelf, and as you said, like $30 million per day, only one facility. And if you can save them one day, actually you can make a big difference there. So yeah, I would like to stop here if you have questions. So, thanks.